little bit about polynomials, divisibility of polynomials, and now first talk a little bit about Euclidean rings and principal ideal domains, and then about irreducibility of polynomials, and we'll be almost finished with that, and next time then we will start with fields. So let me first talk about Euclidean rings. So we had seen one examples that in Z and in the polynomial ring with coefficient in the field we have division with rest. And so the ring in which we have the same, so we want to formalize this when you make division with rest, then somehow the rest should be smaller than the thing you divide by. And so you somehow have to measure this, and this is will be measured by a certain function d. So let me make the definition. An integral domain is called, I just say Euclidean ring, so it's alphabetical domain. If we have the following, if there's a function d from the non-zero elements in R to the non-negative integers, which two properties, well, usually one only uses the first, but sometimes one needs the second. So first, so if we have two elements, so then we can divide one by the other with rest, such that the d for the rest is smaller than the thing you divide by. So there exists Q and R with A is equal to QB plus R, and d of B, d of R is smaller than d of B or R equal to 0. Okay? So we have this property, so somehow with D we measure that in a certain sense the rest is smaller. And the second one says that it's not too trivial, so if B is an element dot 0 is not a unit, then DAB is bigger than D of A for all A in R without 0. Okay. So, okay, so that's simple. So we know some examples. So if we take the integers with d of n is equal, for instance, the absolute value of n, this is a Euclidean ring. Because we can take can divide an integer with by another, and the rest will be smaller than what we divide by. And if we look at kx and d of f is the degree of f, this is also Euclidean. Because this is we have seen, this was the division with rest, that we can always divide the polynomial f by another polynomial in such a way that the rest has smaller degree, always 0. So that's fine. I want to at least give one more example, which is the Gaussian integers. So set E, set of all n m with the n and m integers. So this is the subelement of the complex numbers, so the Gaussian integers. And I claim this is also Euclidean ring. So in this case, we can, for instance, take d of n plus im to be, what is it, n squared plus m squared. I should say that Euclidean rings are somewhat rare, so it's not that every integral domain will be a Euclidean ring, but we have some such examples. And so why is that the case? So we have to show that we can fulfill these properties. So the second property is kind of trivial because we know that the units in ZE is just 1, minus 1, I and minus I, and you can easily see that if something is not 0 and not a unit, then, well, anyway, we'll see it in a moment. So because the main property is the following, so we can extend d to the complex numbers by saying d of a plus b is equal to a squared plus b squared, which is also the square of the complex absolute value that you learn in complex analysis. And there, one can, so, and from there you know that if I take product of two complex numbers, d of a, maybe, yeah, whatever. Now these are complex numbers, d of a times b is equal to d of a times d of b for a, b complex numbers. Anyway, if you haven't learned it, you just compute it, no? It's not too difficult. So this, for one thing, shows that this second property of D is kind of trivial because so the units are precisely these. You can see these are precisely the elements such that D of the element is equal to 1. And so so these are the only ones such that if you multiply, so therefore this is the only case that D of AB, which is dA times dB, is equal to dB, otherwise it's always bigger. So that was the second property. But more interesting is the first property, namely, and let's see. So now we want to make division with rest in Zi. So let Z and W be elements in the ring of Gaussian integers, and you want to make the quotient. So we can first, so what can we take as quotient? So we can first take the quotient in the complex numbers. Be the quotient, so in C, and be the quotient in C. So we know how to divide two complex numbers by each other. And now the kind of quotient in here, where there will also be rest, will be some kind of approximation of this, the closest number. So how do we do this? So we choose n and m and z such that, so maybe I write this as a plus ib. Okay? So this quotient is so where a and b are some real numbers. So then we choose n and m and z such that if I take so the absolute value of a minus n, this is smaller or equal to 1/2, and the absolute value of b minus m is smaller or equal to 1/2. Obviously, you can always do this. If you have real numbers, you can the nearest integer will be at most 1/2 away. And so we will want to say that so we want to take n plus im to be the quotient, and we want to see that the rest is not too big. So let's see. So if we now take, well, how far are we away from the quotient? If we take z divided by w minus n plus im, well, this is, you know, we take this is a minus n squared plus b minus m squared, which is smaller or equal to 1/4 plus 1/4. Okay, so the distance, so this is at most 1/2. And now we put the quotient to be n plus im, and the rest to be whatever is left over. So this is z minus w times q, and we want to see that this satisfies this condition. Okay, so let's compute. Then, so obviously z is equal to w q plus r, as we wanted in the condition. What can we say about r? So d of r is equal to d of w times d of z divided by w minus q. And this z minus by this we had precisely seen. This was most 1/2. So this is smaller or equal to 1/2 times d of w, which is smaller than d of w.
Excuse me.
Yeah?
Maybe, is it 1/2 of or 1 over square root of 2?
What? No, one takes the square.
Okay.
No, here it's with the square. Obviously, I should also. Okay, and so it's equal. Okay, so this was this little case. Another property which is related is that of being a principal ideal domain that we will use. So we know ideals in rings, we know the ideal generated, where principal ideals are ideals generated by just one element. And in some rings, every ideal is a principal ideal. These are called principal, and if they are domains, then they're called principal ideal domains. And you will see in a moment that Euclidean rings are principal ideal domains. So, definition. A principal ideal domain R is an integral domain in which every ideal is principal. So that means it's so every ideal is going to be I. So I can always write I into the ideal generated by one element for some in R. Okay, so obviously this seems a strong property. We have to see that this even exists. And the first result is that Euclidean rings are principal ideal domains. So that's quite simple. Basically, you somehow, in a suitable sense, have to find the smallest element in a ring and to regenerate it. So you take the element with the smallest d of A and be the generator. So let's see. So I take an ideal in R. So if I is the zero ideal, then I is the ideal generated by zero. So that means principal. So thus we can assume that I is not the zero ideal, and so we can choose an okay. So now we can, as I said, we choose an element which has the smallest possible d. So let A in I, a non-zero element, such that d of A is equal to the minimum over all the numbers d of B, where B runs to the non-zero elements of I. Now, so the D assigns a non-negative integer to every element in the in the ring without zero. So obviously, so the set of all D of B with B in this is a set of non-negative integers, so it certainly has the smallest element that we can take. And so the claim is obviously that this element regenerates. And that's also quite simple. So then I is equal to the ideal generated by A. So if not, then there is this element B in I, which is not in the ideal generated by A. So we can make division with rest. So we divide B by A. The B is equal to Q times A plus R with either overall with R equal to r equal to 0, but then it would divide it. So with d of r smaller than d of, I actually need to make an indirect argument, but anyway. However, this contradicts our assumption that that this should be so actually it was, in some sense, I didn't need an indirect argument. I could just say take any b and I, and the division with rest gives it is like this, with either r equal to 0 or this is smaller, and it cannot be smaller, so r is 0. So that's maybe slightly more less twisted argument. But anyway, still okay.
And is it always possible to find minimum of dB?
Is it what?
It is always possible to find the minimum of the set.
Well, this is a set of non-negative integers, so it's
Integers.
these are non-negative,
Ah,
so the map D
Yeah,
was
I
to the
made it.
non-negative integers, so it's certainly possible to find that. Okay. So in particular we see, so find that Zi and Kx of K field are principal ideals. So maybe I should say the abbreviation is always PID, not because it's principal ideal. So we also can see that in a principal ideal domain, we always can find the greatest common divisor of any set of elements. This is some simple fact. So if R is not guaranteed that you always have the greatest common divisor in an integral domain, but in a principal ideal domain it's easy to find. PID. We take some elements and then there is a greatest common divisor of A1 to AN, of A1 to AN. So what I want to say more. Okay, and in fact it's very simple again. So I mean it's kind of obvious. We take this generates an ideal. So this is a principal ideal. The generator of this principal ideal will be a greatest common divisor. So let's see how. So we choose D such that in R such that the ideal generated by A1 to AN is equal to the ideal generated by D. So we know what the principal ideal is. Then, by definition, A for I from 1 to n, we have that AI is in the ideal generated by D, which is just the same as saying that D divides AI. So that means D is a common divisor. Of these elements, and on the other hand, we know what these elements look like. So Now, as D is an element in A1 to AN, it means we can write it as a linear combination of these. We can write D equals sum I equals 1 to N Ri AI with Ri some elements in R. So if we do have a common divisor of all of them, so if T in R is a common divisor, of A1 to AN, then it divides all of the AIs, so it divides the sum, so it divides the okay, and so D is a great common divisor. Okay, so these were all rather trivial facts, but we just wanted to no. Okay. So now we want to talk about irreducibility of polynomials. We will later one uses irreducible polynomials with coefficients in the field to construct some field extensions to make bigger fields from smaller fields, and so therefore we want at least a little bit study how one can check whether a polynomial is irreducible. We just do a few things, but at least a few tricks or a few criteria. I haven't yet told you what irreducible means, but it means it will mean that you cannot write in a non-trivial way as a factor, as a product of two elements. Irreducibility of polynomials. As I said, an element in an integral domain will be called irreducible if it cannot be written in a non-trivial way as a product of two other elements. So that means, so if this element is called A, if A is equal to B times C, with B, C elements in R, then you can always divide by units, so then it follows that B or C is a unit. And then we will want to study this for polynomials. We want to know when polynomials in the ring Kx are irreducible. And so maybe I wouldn't have written it once because I now write it again. So we'll study this for polynomials f in Kx. And so actually I will just do it in the case of Q and Zx. Okay, so maybe I should properly write the definition. Let R be an integral domain. So as I said, Q in R, which is not 0, is called irreducible so if it's not a unit, And as I wrote before, whenever I can write Q equal to A times B, with A and B and R, it follows that A of B is the unit. Then A is a unit, or B is a unit. Okay, now we want to see and so otherwise it's called reducible. Because I meant Q is called reducible. So it is reducible when if I can write Q equal to AB, where both A and B are not units. So examples. So for instance, so if I take an element, an integer Q, then Z is irreducible if and only if Q is equal to P, or Q is equal to minus P, or P of prime. No, because so this with minus P is because the units are plus or minus 1 in the integers, and a positive integer is a prime number that cannot be written in non-trivial way as a product of two integers. So if field K has no irreducible elements, well, trivially, because obviously every element is either a unit or it's 0. So cannot even start. And so one example for an irreducible polynomial so if K is a field, with K be a field, and so F in Kx. Well, I just do. And I take just look at one thing. So I take A in K without 0, B an element in K. Then it follows that AX plus B is irreducible. In Kx. And that's clear if we write AX. So if you write AX plus B equal to F times G, then it follows that 1, which is the degree of AX plus B, is equal to the degree of F plus the degree of G. So it follows that one of these two numbers must be 0. Or degree of G is equal to 0. So that means, for simplicity, you can assume that, say, degree of F is 0, then F is a constant, so an element in K. If this constant were 0, we would have that already this had to be 0, which is not true. So this is a non-zero constant, so it's a unit in K. Okay. One further thing that we have is that if we are in a principal ideal domain, then the ideal generated by an irreducible element will be a maximal ideal. Here D and P in R irreducible, then it forms the ideal generated by P is the maximum. Again, this is basically the definition. So anyway, remember that the maximal idea, so the irreducible element will always generate a maximal idea. So what it means is it cannot be contained in a bigger idea which is not equal to R, so that I in R be an ideal with P contained in I. We have to see either P is equal to I or I is equal to R. So, as it's a principal ideal domain, we can write I equal to the ideal generated by some element A. And that P is contained in I means that A divides P. I can write it as a multiple, or I can write P as a multiple of A. So that means, so P is equal to B times A with B and R. Now, but as P is irreducible, we have two possibilities. One of these two must be units. So either B is a unit. We know that the ideal generated by something and by something multiplied by unit is the same, so it follows that P is equal to this A, which is I, or A is a unit, and we know that the ideal generated by a unit is the whole of R. And so altogether we see that the ideal P was a maximal ideal. Because any ideal which lies between it and R must either be equal to it or to R. Okay, that was also simple. Now, the application that we will use this, as I said, to construct field extensions. So let me just take this as a corollary. So let take the field F, a polynomial with coefficient in K, which is irreducible. Then Kx divided by the ideal generated by F is a field. And I should say, I write it loosely, containing K as a subfield. in strictly speaking, it contains a field isomorphic to K as a subfield. So subfield just means it's just subring, which is also a field. So, so let's see it. So we know that F is irreducible. Thus, F is a maximum ideal. In Kx, and thus Kx modulo F is a field. We want to see that in a suitable sense we can find K in it. I mean, as I said, a subfield isomorphic to K, which we can, if you want, identify with K. So if we look at the natural homomorphism, the natural projection, so from Kx to pi, x modulo F, so this is the natural projection. If we restrict it to the constant polynomials K, it is injective. So restrict it, so to have this natural projection of P restricted to K equal to constant polynomials. So from K to Kx modulo F is injective. Anyway, as it's a homomorphism of fields, it would have to be either the zero map or injective, but it's anyway injective because the kernel of P intersected with K is just 0. No? The multiples of F, which are constants, are just 0. And so this does the Kp is taken to K from K to say P of K in F is an isomorphism. Okay. And no, it's natural to identify K in an image of the complex of the constant polynomial, so that you can say that this thing is a field which contains K as a subfield. And so this will allow us to, given an irreducible polynomial, we can always make a bigger field. We'll use this some point later. Okay. So now, as it will turn out that irreducible polynomials are useful, or it's important to know whether a polynomial is irreducible, I want to give a few criteria. So, study reducibility of polynomials. So I want to make a few criteria. That's here. So, and I want to do it, as I said, in, so polynomials either with coefficients in Z or in Qx. One could do this in more generality, where this Z is replaced by a ring with a certain property. One would need that it's what is called a unique factorization domain, which I haven't explained to you what is. And this would be the quotient field. Then if we define what this is, then the same arguments I'm going to give work the same way. But I just do it in this case where you can see some more everything. So definition So the thing is basically we want to study irreducibility of polynomials with coefficients in Q, but it turns out surprisingly that the criteria that we have are always for polynomials with coefficients in Z. And so we also have to compare what it means for a polynomial to be irreducible here and here. Okay?
No, I haven't really understand this.
What?
I haven't really understand your explanation about the comparison between.
So, I mean, in the moment I haven't said anything, I just said what we are up to. But so, we want to study irreducible of polynomials. So when a polynomial in Zx is irreducible in Zx and in Qx, we want to compare this. So when this is the same or different. And then later we will give one criterion for a polynomial to be irreducible, and this will be for coefficients for polynomials in Zx. And for this to be useful for us, we need to know that this then implies it's also true here. And so and this is true if the polynomial is primitive. So let me write this down. A polynomial f some I equals 0 n ai x to the I is called primitive if the coefficients are relatively prime. So if the coefficients, if a0 and an are relatively prime. So that means that a greatest common divisor of them is 1. So for instance, if any of the coefficients is 1, then the certain is the case. And now we have the first lemma, which is currently due to Gauss, which says that if a polynomial with coefficients, so a polynomial with coefficients in Z is primitive, which is primitive, is irreducible as a polynomial in Zx if and only if it is irreducible here, which is exciting fact. So, but first we have another lemma which looks simpler. So we take two polynomials with coefficients in Z which are primitive. Then it follows that the product okay, so that kind of looks like it should be obvious, but it actually requires a little proof. So let's try to do it. So we want to see that if there's no common factor of the coefficients of f and no common factor of the coefficients of g, then also there's no common factor of the coefficients of f times g. So we write down the coefficients. So f, let f equals some I equals 0 n ai x to the I and g put some I equals say j equals 0 to m dj x to g. Okay. And so we assume that f times g is not primitive. And then we have to see that no, either f or g is not primitive. So f g is not primitive. So follows there exists a prime number p which divides all coefficients of fg. So that it's not primitive means there is a greatest common divisor of the coefficients which is not 1 or minus 1. So we have a greatest common divisor which is some so particular so we have a greatest common divisor which is a positive integer which is bigger than 1, and certainly this greatest common divisor is divisible by some prime number, and so that will divide all the coefficients. And now we want to see, let's see. But we know it doesn't go, this prime number will not divide all the coefficients of f and not all the coefficients of g. So let ai be the lowest degree coefficient of f such that p does not divide ai. And this thing, and in the same way, Vj, the lowest degree coefficient of g, such that p does not divide Vj. Then, I mean, the obvious question is, what happens to the coefficient of fg of degree I plus j? That seems to be. So what is the coefficient of x to the I plus j of fg? We can compute it. So this by itself is the sum over all IL EM such that L plus M is equal to I plus j. So we can write this. So I write this coefficient as Ci plus j, which is equal. So one way is that we have ai times bj, or this number is bigger than I and this one is smaller than j, or the other way around. So plus some k bigger than I, ak b I plus j minus k, plus the sum of all k smaller than I, ak b I plus j minus k. Oh, so this is all the possibilities. So what do we see? So we see that p divides, so this was the lowest degree for which it doesn't divide it. So if k is smaller than I, then p will divide ak. So p divides ak for k smaller than I, and p divides b I plus j minus k for k bigger than I. Because if k is bigger than I, then this index is smaller than j, and so therefore it will, as this is then smaller than the lowest degree for which it doesn't divide, it divides. So therefore we see that p divides every summand here and every summand here. It does not divide this one, because it divides neither ai nor bj, so it cannot divide this one. P divides every summand in both sums, but not ai bj. And so if you want, you can bring it to the other side. If it would divide this one, then ai bj would be this minus this, and that you would divide every term on one side and not this term. So it follows plus P does not divide C plus J. So we see that if a polynomial is the product of two primitive polynomials is primitive. Now this is maybe not such a difficult lemma to the name of Gauss, but it was used to prove the next statement, which is also called Gauss lemma. Namely, let's take that f in Zx be a non-constant primitive polynomial. Then f is irreducible in Z of x if and only if f is irreducible in Q. And that's actually somewhat surprising because, to be reducible, it means we can write it as a product of two things. And here in Qx there are many more polynomials than there are in Zx. So it would seem it's much easier that the thing is reducible in Qx than in Zx. But the claim is if the polynomial is primitive, it's equivalent. So the fact that we allow coefficients in Q does not help us to find the factor. That's one direction, the other one is kind of trivial. So we start with the easy direction. So basically, let's assume that f is reducible in Zx. Then it's quite almost immediate from the definitions, as we know that it's primitive, that it will also be irreducible in Qx. Namely, so it follows, you can write f equal to g times h, with g and h polynomials in Z. And both g and h are not units in Zx. So, if the degree of one of the polynomials is 0, now, obviously I can choose which one is equal to 0, then G is a non-unit in Z. So, which is a common factor of the coefficient of f times g. This was g of f equal to g times h. And so it follows that f is not primitive. So we cannot have a common factor of degree 0, because that would make the thing not primitive. And so thus the degree of g is bigger than 0, and the degree of h is bigger than 0. And so f and g and h are both non-units also in Qx. and so F is reducible in Q. So this is kind of easy. We just we needed this primitive in order to exclude these idiotic things that this polynomial is a common factor. I mean, this constant polynomial is a common factor of all the coefficients, but otherwise there's nothing there. And now let's look at the other direction.
Please, how the fact that the degree of G and degree of H are positive imply that G and H are non-unique?
So we know that we know that the units in the polynomial ring are equal to the units in R. So that means if so this is R. So this means I take a constant polynomial of degree 0, whose constant coefficient is an element in R, which is a unit. And so if a polynomial has positive degree, it never is a unit. You can also see, I mean, in polynomials, you cannot find the inverse of it. Okay, now let's look at this. So now we instead assume this thing that we can write F as a product of two polynomials in Qx. So suppose F is equal to G times H with the G and H in Qx of positive degree. And now we have to see, we can find the same kind of thing where with maybe with different G's and H, where now these have integer coefficients. And that's actually, so what we do is we clear the denominators. So we multiply with say all the denominators in the coefficients AI of F, and then we divide by the greatest common denominator of the new coefficients. So to find, say, the G prime in Zx with the G prime is equal, say, to A times G, where say A is in Q, and in the same way, and G prime is primitive. In the same way, find F prime in Zx such that F prime is equal to B times G with B in Q. What? This was H, no? H prime. H prime is primitive. And so obviously it follows that F is equal, what is it, to, what is it now, it's 1 over AB times G prime H prime, where these are some primitive polynomials. So for these things I just have put out. So AB is some 1 over AB is an element of Q, so we can write it equal to C divided by D, where C and D are integers which are relatively prime. And we just divide out the common factor. So that means, so in other words, we have f is equal to c divided by d, g prime, h prime, or equivalently, df is equal to c times g prime, h prime. Now, as f is primitive, we had assumed that f is primitive, it follows that the greatest common divisor of the coefficients of d times f is d. And this is one greatest common divisor. One greatest common divisor. We had 1 as a greatest common divisor before. If you multiply the whole thing by d, d is a greatest common divisor. And we have g prime and h prime are primitive, so g prime and h prime primitive means a greatest common divisor of the coefficients of c times g prime h prime is c. Now these two things are equal, so it follows. So these are, the coefficients of this, this is the same thing. So the greatest common divisor, so thus the greatest common divisor is well defined to multiplying by a unit. So it follows that C is equal to plus or minus D. So thus we have that F is equal to G prime H prime, or F is equal to minus G prime H prime. And in any case, we have found that it's a product of two primitive, of two polynomials of two polynomials with coefficients in Z. So it's irreducible. It's reducible. In Zx. So you see that this kind of trivial observation that if f is primitive, if I have a product of two primitive elements, then its primitive is somehow comes here to a non-trivial consequence.
How we know that G dash and H dash are primitive?
What?
G dash primitive.
So so primitive means that the greatest common divisor of the coefficients is one greatest common divisor. It's 1. So first, originally this thing has coefficients in Q, so I just multiply by all the denominators. So then now I have a polynomial with coefficients in Z. Now I just divide all the coefficients by the greatest common divisor, by their greatest common divisor. Then afterwards the greatest common divisor is 1. And that's how I define H prime. So I first multiply with all the denominators, and then I divide by the greatest common divisor of the new denominators. And so altogether I have multiplied the whole thing by some rational number. I don't care which one. And I get a primitive polynomial. It's always, if you have a polynomial with coefficients in Z, you can always divide by the greatest common divisor of the coefficient, you get a primitive one. And if you have a polynomial with coefficients in Q, you can always clear the denominators, you get a polynomial with coefficients in Z. Okay. Yeah. Now I want to use this to give the standard criterion for irreducibility, which is the Eisenstein criterion. Maybe, okay. So we take, so let F in so sum AI xi be a primitive polynomial of positive degree. So in polynomial with coefficients in Z, primitive of positive degree. And I make the following assumption. Assume there exists a prime number P which divides most of the coefficients. So P divides A0, P divides A1, and so on. P divides an minus 1, but it doesn't divide the leading coefficient, and P squared does not divide A0. Then it follows F is irreducible in Zx and therefore also in Qx. So okay, so this criterion has the advantage of being so simple to state, and it's something, if you see a polynomial, you can immediately see whether it's true or false. The disadvantage is that it doesn't apply so incredibly often, no? Because you have to have precisely this. But you know, it's one nice criterion where you just have one glance and you see whether it's true or false. So just yeah. So we see that in a moment. And now let's try to prove it. So we basically again have an indirect argument. So obviously the sum went from 0. So we write f as a product of two polynomials, and then we have to see that one of them must be a constant polynomial. So assume f is equal to g times h, where g and h are in Zx. We have to show that g is plus or minus 1, I mean the constant polynomial plus or minus 1, or h is equal to plus or minus 1. I have to somehow use this. So somehow we do this by worrying about which coefficients of g and h will be divisible by p. So let's look at it. So I write g equal to sum I equals 0 n, no, not n, or the number is k, bi x to the I, and h equal to sum j equals 0 to l, and then cl x, so c j x to the j. Where I assume that this is actually the degree, so dk is different from 0 and cl is different from 0. And then obviously k plus l is equal to n. So we know that a0, the constant coefficient here, is just the product of the constant coefficients of these two. And we know that P divides A0, but P squared does not divide A0. So that means P can only divide one of the two factors. If it divides both B0 and C0, then P squared would divide A0. So it follows that P divides precisely one of B0 and C0. And we can assume, because obviously it's up to us whom we call G and whom we call H, so we can assume it is B0 which is divided. So we say P divides B0 and P does not divide C0. We know, if you multiply it out, that AN is equal to BK times Cn. The only way how we can get the highest order coefficient is by multiplying higher coefficient. And P does not divide AN, so it follows that P cannot divide BK. So we know that P divides B0 and it does not divide BK. So if we go from B0, B1 and so on, there will be the first time it doesn't divide it. It divides B0, maybe it divides B1 or not, and so on. But at some point it will stop dividing everybody. So therefore, thus there exists. We can close the door. And there exists a J, which must obviously lie in 1 and K, because it's not B0, such that P divides BI for I smaller than J, but P does not divide Bj. It's the first one it does not divide. So what can we say about this? So I mean, can also already say the punchline. We finally see that this whole story, if one looks at it carefully, implies that this J must be equal to N. And that means that H must be constant. But okay, let's get to that.
That argument that P divides P naught but divides PK, it's okay. What was the story?
Where are you? Oh, so here.
Yeah.
So we have seen that P divides P0.
Yeah.
And it does not divide PK. So therefore, it cannot be that it doesn't divide all of them. So there will be a first time so that it doesn't divide everybody that comes before. So it might be that it doesn't divide B1, then this J will be equal to 1. But if it divides B1, then maybe it doesn't divide B2, then J will be equal to 2. In the worst case, it divides everybody but not BK, then J will be equal to K. So let's look at the coefficient AJ. So AJ, so for this J, AJ we can write it as BJ C0 plus BJ minus 1 C1 plus and so on plus B0 CJ, where we, if it could in principle be that if L is smaller than J, we just put these equal to 0, no? So we can write it like this. And what do we know? So we know that it's in some sense the same argument as we had before. P does not divide Bj C0. Because P does not divide Bj, because that we have assumed here, and P does not divide C0, because that we had before. But P divides all others. Because here it divides Bj minus 1 and so on until B0, and so divides all others. So if it doesn't divide this, and it divides all of these, it does not divide this. So thus, P does not divide Aj. But now that's a rather big thing, because we had said that P is supposed to divide all AI except for An. So that means J is equal to N. And so that means in particular it follows that the degree of, so therefore K must be equal to N. So thus the degree of G is equal to N and the degree of H is equal to 0. So H is an element in Z. And as we have assumed, as our polynomial was primitive, as f is primitive, it follows that h must be equal to plus or minus 1. Okay, so it's a bit strange to do all these things which don't seem to lead anywhere, and then all of a sudden it's finished. But it's obviously built up like this. Okay, so this was the statement. So it's very easy to apply. When it applies, maybe I should have. There are also many variants of it. You can modify the statement a little bit and it's still true. Maybe I should have given you one such as an exercise, but anyway, now I didn't. So example. So if I take f equal to, say, x to the 5 plus 4x plus 2, obviously this is irreducible by the Eisenstein criterion for the prime number 2. And you can see in this example that it's really trivial to check. One example that we will use later is that if for p a prime number, if I look at x to the n minus p, this is also primitive. In fact, obviously, if p is not, so obviously, if you have x to the n minus m, where there's one prime number which only divides it to the first power, then it is not primitive, irreducible by the Eisenstein criterion for p. There are some simple examples. So I don't quite finish, but anyway, so there are some other trivial criteria. So, for instance, the following remark: if f, say in where we want it to be, x or whatever is s degree 2 or 3, then well, if it is to be 2 or 3, then if it is not irreducible, then it follows that f is equal to g times h, where one of the factors has degree 1. So thus, if it's for instance g I can write as ax plus b, and then minus b divided by a is 0 of f. So we can see if the degree is 2 or 3, then if it doesn't have a 0 in K, this is irreducible. And there's this exercise that I gave you. If I now assume that I have a monic polynomial with coefficients in z, so if now f in zx is monic, so that means the leading coefficient is 1. So that is f is equal to sum is x to the n by sum I equals 0 to n minus 1 ai x to the I. Then we have the exercise. Any 0 of so this actually is not Qx, it's just any field. Then okay, any 0 of f must be in Q actually, so lies in Z, any 0 we will call it A, and we will call it B, and B divides A0. So in particular, therefore, if for instance thing has degree 3, a very stupid way to see whether it's irreducible, if the coefficients are in Z, then, so if it's reducible, it must have a 0, and this 0 must be a divisor of the constant coefficient, so there's not very many cases to check. There's some let me see. Well, maybe I will not. There's one more example, but maybe I will stop now. Anyway. Okay, so maybe.